All right, let's get started with this part of the video. So, as I mentioned at the start of the implicit differentiation video, in the calculus scope and sequence at Yes Prep, Unit 7 is implicit differentiation and differential equations. Differential equations is just a favorite topic of mine. I loved it when I was in college. We used it in so many of the physics courses that I took. It's so rich with application problems. But in this video, we're going to focus on some of the skills that we needed to develop in this unit. So let's just jump into this. There are two kinds of differential equations that we studied. There are the simple differential equations, but what I mean by a simple differential equation is that, first of all, a differential equation just means an equation involving derivatives. Okay, we might be looking at the first derivative, we might be looking at a second derivative, but we're looking at an equation involving derivatives. And in order to solve it, our goal is to get back the original function. So our final answers are usually y equals something or f of x equals something. Some of the vocabulary terms that we picked up in this unit, let's see, we have f double prime of t equals the sine of t plus cosine of t. Because we're talking about a second derivative, this is sometimes referred to as a second order differential equation. Not too worried about the vocabulary terms. F prime of pi equals 0, and that f of pi equals -3. These are often referred to as the initial conditions. And so my goal, f of t is going to be my solution. So let's see, what do we know? We are given f double prime. I want to get to f, and in between f and f double prime we have the function f prime. If f double prime is the function that I know, that's the function that I'm given, I can move up to f prime by taking an integral, an antiderivative. I can then move from f prime up to f, again, by doing an integral. So if I'm given the second derivative, and I want to get back to the original function, we're going to have to integrate twice. Simple differential equations are the kinds of differential equations where this just integrating or taking an antiderivative is what's going to get you to your final answer. Later on in the video, we'll talk about separable differential equations that require a little fancier moves. So, since f double prime is sine of t plus cosine of t, let's take one integral to get to f prime. F prime is going to be the integral of the sine of t plus the cosine of t. T is my variable, so I'm integrating with respect to t. The antiderivative of the sine of t is negative cosine of t. The antiderivative of cosine of t is the sine of t. And whenever we do an antiderivative, if we're doing an indefinite integral, we're going to bring in Charlie. So the first derivative can be written as negative cosine of t plus sine of t plus Charlie. If I am not given any other information, I might need to stop here. But I was given that f prime of pi is equal to 0. So another way to say that is when t is equal to pi, then the derivative is equal to 0. Well, let's use that. So that means that if t is equal to pi, f prime is equal to 0, I can rewrite my derivative as 0 equals negative the cosine of pi plus the sine of pi plus Charlie. The cosine of pi is -1, so negative cosine of pi would be positive 1. The sine of pi is 0, and then we have Charlie. We should get that your constant of integration, or what we lovingly call Charlie, is -1. Because of that, we can pronounce that f prime of t must be of the form negative cosine of t plus sine of t minus 1. And that's good. We've actually done this in some previous units when we first learned about the antiderivative. We just didn't necessarily call it a differential equation. We didn't mention initial conditions, but this is what you do. We're not done because we want f of t. Well, if I'm at the first derivative and I want to get to f, we're going to integrate again. So we integrate negative cosine of t plus the sine of t minus 1. We're going to integrate with respect to t. The antiderivative for negative cosine is negative sine of t. The antiderivative for positive sine will be negative cosine of t. The antiderivative for negative 1 is going to be negative t, plus another constant of integration. And since this is the second time where I'm seeing c is showing up, I'm going to refer to it as c2. So this is f of t. I would call this solution here a general solution. This is a general solution because we haven't actually figured out what our constant of integration is. Of course, we can do that if we use our other initial condition. F of pi is negative 3. So let's use pi and negative 3. Negative 3 equals negative sine pi minus cosine pi minus pi plus c2. Let's see, sine of pi is 0, cosine of pi is negative 1, so that becomes positive 1, minus pi plus c2. Now pi is a number. That means I can add pi to both sides, just like I normally would with any other number. I can subtract 1 from both sides, and so what I'm going to get, the 1's will cancel out, the pi's cancel out, c2 is equal to negative 4 plus pi. Now, before you box your answer and move on, let's keep in mind the question was, or the statement said, find f of t. So my final answer, f of t, will be negative sine of t, negative cosine of t, minus t plus Charlie. That's this negative 4 plus pi. That final answer, because it doesn't involve our constant of integration, is what we refer to as a particular solution. No longer a general solution, it's a particular solution. Some authors refer to it as a specific solution. Over the course of this unit, students have gotten really good at solving these simple differential equations. So let's try a harder one. Okay. It is known that y equals a times the sine of, technically this guy here is called omega, O-M-E-G-A, last letter of the Greek alphabet, omega times t. And omega is, we're going to be using that as a constant in this case. If you don't like referring to it as omega, call it w, that's fine. But we are told that this y equals a sine omega t is a solution of the differential equation d squared y dt squared plus 16y equals 0. Using this information, we want to find the value of omega. For this problem, we're going to assume that omega and a are both constants. So here's how we normally approach a problem like this. If we know that this is a solution, we're specifically given that the function is a solution to the differential equation, then what that means is I can plug, that sounds horrible, I can plug this function into the differential equation and I will get a true statement. So let's see. If y equals a sine omega t, and I take the first derivative, since a is a constant, I don't need a product rule, and we know from derivatives that y prime should be a times the cosine of omega t, careful, don't finish it yet, times omega. Because what did we just do? We did the chain rule. The derivative of sine omega t is cosine omega t times omega. I can rewrite that as a times omega times cosine omega t. Let's take another derivative. The a and the omega are constant, so we leave them alone. The derivative of cosine is negative sine omega t, again, times omega. I can rewrite that as negative a omega squared sine omega t. We haven't actually used the differential equation yet. We're just getting all the players on the field. We need y. We don't necessarily need y prime in the differential equation, but we do need y double prime. That's this d squared y dt squared. So, if d squared y dt squared plus 16y is equal to 0, then that means if I take my second derivative, negative a omega squared times the sine of omega t plus 16 times y, that y is a sine omega t, that's supposed to be equal to 0. And what's implied in this problem is that this is always going to be equal to 0. The goal is to show that that is a solution. No, I'm sorry. The goal is to find the value of omega that makes this true. Sorry about the awkwardness there. So I've got an equation. I'm going to set it set equal to 0. Let's see. I see a sine omega t over here, a sine omega t over here. I can factor that sine omega t out. What that'll leave me with is a negative a omega squared plus 16a is equal to 0. I guess I technically could have factored an a out as well, so let's do that. A times sine omega t negative omega squared plus 16 is equal to 0. All right, so when is it that this expression over here is going to be equal to 0? Well, let's see. Since this is all multiplication, that means that a is equal to 0. Sine of omega t is equal to 0, or negative omega squared plus 16 is equal to 0. Well, we were told earlier in the problem that a is a positive constant. Since a is a positive constant, this can't be true. Sine of omega times t is equal to 0. Well, that can happen a lot. But what we're looking for is a solution that doesn't depend on t. So we're going to skip over that. I think that was a little hand wavy on my part. What I want to focus on is over here. Negative omega squared plus 16 equals 0. I can rewrite that as omega squared is equal to 16. Taking the square root on both sides, I get that omega is equal to positive or negative 4. Again, we were told in the beginning that omega is a positive constant, so the negative version is not allowed, and omega is equal to 4. All right, let's move on. Okay, here's another typical question that we come across with these differential equations. Sometimes we are told to show that a function is a solution to the differential equation. Basically, you could use that word verify, replace it with the word prove, like we would have proved trigonometric identities back in pre-calculus. Sometimes it'll show up as show. You want to show that this is a solution to that differential equation. Basically, again, it's just like the last problem. We're going to take this function over here and plug it into the differential equation. And although it's not explicitly stated in the problem, C1 and C2 are indeed constants. Okay. Bad planning on my part. I should have mentioned specifically that those are constants. But I want to show that when I actually evaluate this differential equation, that this function will actually be a solution. So let's see. I see x times y double prime plus y prime equals 0. So that implies I need a first derivative. Since c1 is a constant, its derivative is 0. This c2 is being multiplied by the natural log, so the derivative here is c2 times 1 over x, because we know the derivative of natural log is 1 over x. If I take another derivative, I have c2 times the derivative of 1 over x is negative 1 over x squared. If you'd like to, you could clean these up. c2 times 1 over x is the same as c2 over x. c2 times negative 1 over x squared is negative c2 over x squared. So let's look at how we're going to show that this function is indeed a solution. So just like we would have done back in pre-calculus, we normally start on one side of the equation and working only with that one side show that when I plug in the values for y prime and y double prime, that my result is going to be what's on the right-hand side. So left-hand side says take x times y double prime. Well, y double prime is this negative c2 over x squared. I want to add to that y prime, which is c2 over x. And I'm not going to write that it's equal to 0 because we are being asked to show or to verify that this is equal to 0, which means we have to restrict ourselves to working on this one side of the equation. Let's look at this. X times negative c2 over x squared plus c2 over x. I have an x in the numerator and x in the denominator. I can cancel those out. That gives me negative c2 divided by x plus c2 divided by x. Well, let's see. Those have a common denominator. That gives me negative c2 plus c sub 2 over x. I get 0 divided by x, which is equal to 0. That's the right-hand side. That is exactly what I was being asked to show. It's a relatively short one. Lots of my students are fans of ending it with a smiley face. Some people like to write QED for quod erat demonstratum. Whatever, okay? Writing that is not the important piece. It is important that we work on one side and make it appear algebraically, show that it's equivalent to what's on the right-hand side. All right, so now let's look at this one. If dp dt equals 10 e to the t and p of 0 equals 25, for what value of t will p of t equal 20? Now, I think really this would have been better expressed in a word problem. Maybe p stands for population. Yeah, I kind of like that. And so we could state dp dt. This would tell you how your population is changing. So we might say something to the effect of the population of a town is changing at a rate of 10 e to the t people per year. We would need some units. P of 0 equals 25. Another way to say that would be your initial population is 25. For what value of t will P of t equal 20? So maybe this question could be the initial population is 25,000 people, 25 million people. For what value of t will P of t equal 20? For what value of t will the population reach that 20,000 or 20 million? I didn't write it as a word problem. I just wrote it as a differential equation. So let's see. We know dp dt equals 10 e to the t. dp dt just means p prime. If I want to get to p, or the function p of t, we're going to integrate with respect to t. The integral of 10 e to the t is 10 e to the t plus our constant of integration. We're told p of 0 equals 25, so I'm going to plug in the point 0, 25, and we get that 25 equals 10 e to the 0 plus c. E to the 0 is 1, 10 times 1, so c is equal to 15. So my function p of t is going to be 10 e to the t plus 15. Great, that is a particular solution. We figured out our constant of integration. The question is, for what value of t will p of t equal 20? So if p of t is equal to 20, then that means I can write the equation 20 equals 10 e to the t plus 15. We're going to subtract 15 from both sides because our goal is to solve it for t. We get 5 equals 10 e to the t. We'll divide both sides by 10 to get 1/2 equals e to the t. We'll then take the natural log. The natural log of 1/2 equals the natural log of e to the t. We use our favorite property. It's that p in front of the log property. So the natural log of 1/2 is equal to t times natural log of e. Natural log of e is equal to 1. So t is the natural log of 1/2. Depending on the part of the exam you're on, if it's the free response, you can end here. If it's multiple choice, another way you could write the natural log of 1/2 using your properties of logs. The natural log of 1/2 is the same as the natural log of 1 minus the natural log of 2. Natural log of 1 is equal to 0, and so we get that t is the negative natural log of 2. If you have a calculator handy, find natural log of a half. I think it's about negative 0.693. Find negative natural log of 2. You're going to find it is exactly negative 0.693. So either way you want to do it is just fine. All right, so let's keep plowing ahead with differential equations. Okay, now we get to where we spent a couple of days. These are called separable differential equations. A separable differential equation is one, let me write one up here in the top. dy dx is equal to negative x over y. That's an example of a separable differential equation. This is no longer a simple differential equation, and the reason being is we have x and y involved in the derivative. All the ones we did before, it was a dy dx equals some function in terms of x without y showing up. We were able to easily integrate both sides. That doesn't apply here. So the technique, and that's what's outlined on this slide, and I'm not going to read through the whole thing. But your first step is you want to separate the variables. You are going to do whatever algebraic manipulation that you can legally perform so that everything that has a y in it is on one side of the equation, everything that has an x in it is on the other side of the equation. Okay. Once you've done that, we're on step 2, you're going to integrate both sides of the equation. You'll have a function of y on one side, a function of x on the other. You'll have your constant of integration. From there, you normally want to solve the resulting equation for y. So we'll write it in explicit form, y equals blah. If you're given an initial condition, then you will use that initial condition to find the specific value of Charlie, and then you're done. And sort of depends on you. I normally use the initial condition at the end of the problem. Once I've decided, once I'm able to write the equation, the solution as y equals something in terms of x or something in terms of t, normally it's when I reach this point that I use the initial condition. Some people like to use the initial condition after they've integrated both sides of the equation. I'm going to try to remember to do one problem using that first technique, which is solve it all the way to y equals, then use the initial condition. And then I'll do the same problem where we use the initial condition to find Charlie first, then we actually go and solve it. And what you'll see is you get the exact same answer in the end. So it's just one of those things that's sort of left to your discretion. Pick the method you like best. So, here comes the problem. If I can just turn the page. Oh my goodness, what's going on? Alright. Solve the differential equation y squared dy dx equals x to the negative third, subject to the initial condition y1 equals 0. So, y squared times dy dx equals x to the negative third. Okay, I have the y squared and the dy on the left-hand side. I have x to the negative third on the right. I've almost got it completely separated except for the dx. And what we're going to do is we're going to multiply both sides of the equation by dx. It's okay to do that. We've been doing moves like that for a very long time. So now we get y squared times dy equals x to the negative third dx. You've survived step 1 of solving a separable differential equation. You separated the variables. And normally on the AP exam, you're awarded the first point when you get there. Now, we're actually going to integrate both sides of the equation. Well, let's do that. The integral of y squared dy is 1/3 y cubed plus our constant of integration. X to the negative third, I would make it x to the negative 2 divided by negative 2 plus a different constant of integration. So I'm going to refer to the second one as C2 and the first one as C1. And on this problem, we're actually going to do this problem twice. Let's first go about solving it for y. This is what I typically do in class. In order to do that, I'm going to subtract c1 from both sides. We get 1/3 y cubed is equal to, I'm going to rewrite this, x to the negative 2. We can send that downstairs into the denominator. So we get 1 over negative 2x squared. And here's the part that was new for a lot of us. C2 is a constant. It's a constant that I don't know. It could be any number. C1 is also a constant. It could be any constant, any number at all. A constant that I don't know minus a constant that I don't know is a constant that I don't know. This replacement of C2 minus C1 with just C is what we lovingly call Super Charlie. Super Charlie can take on many, many different disguises, and we're going to use it at our convenience so that we don't have to write C2 minus C1, just write big C. All right, my goal is to solve this equation for y, so I'm going to multiply both sides by 3. Y cubed equals 3 over negative 2x squared. Technically, we should write 3 times c. But again, c is a constant that I don't know yet. 3 times a constant that I don't know is still a constant that I don't know. So I'm going to replace that with another Charlie. And it's okay that we're using c again and again. This is pretty typical. Finally, I'm going to take the cubed root of both sides, and because it's an odd root, we don't need the plus or minus. If we stop here with y equals the cubed root of 3 over negative 2x squared plus c, what we have is a general solution. And general solutions are fine unless you're given an initial condition. In this case, we were, so y of 1 equals 0 means that if x is equal to 1, y is equal to 0. So let's use that. 0 is equal to the cubed root 3 over negative 2 times 1 squared plus Charlie. Simplify what's underneath the radical. We get the cubed root of negative 3 over 2 plus c. I can cube both sides to get 0 equals negative 3 over 2 plus c. Add the 3 halves, c equals 3 over 2. Your final answer is that y equals the cubed root of 3 over negative 2x squared plus 3 halves. That is your solution. We've gone from a general solution, and we've ended at a particular solution. That's what we were after. All right. Now, let's do that problem one more time. And this time, instead of using the initial condition in the last step, let's use the initial condition earlier. And what we're going to see is you get the exact same thing. Now, I'm not going to rework the entire problem. What we're going to do is we're going to jump into the problem right after we've done the integration. So we were at, what did we have? We had y squared dy equals x to the negative third dx. We're going to integrate both sides. We get 1/3 y cubed plus c1 equals x to the negative 2 over negative 2 plus c2. I've got that pesky constant showing up on both sides, so I'm going to get rid of that, and I'm just going to leave it as 1/3 y cubed equals 1 over negative 2x squared plus Charlie. The point that I was given, we were told that it passes through the point 1, 0. So if x is equal to 1, y is equal to 0, which gets me 1/3 times 0 cubed equals 1 over negative 2 times 1 squared plus c. 0 cubed times 1/3 is 0. 1 squared times negative 2, divide that into 1, you get negative 1/2 plus c. And c is equal to 1/2. Now, before you panic too much, we are using c differently here. We're saying that c is this guy right here. If I rewrite the problem, I have 1/3 y cubed equals 1 over negative 2x squared plus a half. Let's finish solving this for y. What you're going to do now is multiply both sides by 3. So y cubed equals 3 over negative 2x squared plus 3 halves. There it is. From here we take the cubed root and we get that y equals 3 divided by negative 2x squared plus 3 halves. The exact same answer that we had before. So what's the moral of the story, my friends? The moral of the story is after you've done the integration and you get to an equation like this, before you start solving for y, it is perfectly acceptable to use the initial condition to figure out what Charlie is. Or do it the way I did in the last problem, which is we solved the whole problem for y, and then at the end you use the initial condition. You get the exact same answer both times, so the choice is yours. I generally do the way that I modeled first, but not always. All right, let's pick it up. All right, problem 6. If the rate of change of y with respect to x is inversely proportional to x, and if y equals 2 when x equals 1, and y equals 4 when x equals e, then when x equals 2, y will be equal to what? All right, let's take this apart here. Rate of change. We know rate of change means derivative. For now and forever, amen, rate of change means derivative. But the derivative of what? I want the derivative of y with respect to x. That whole phrase together is what dy dx means. Dy dx is the derivative of y with respect to x. Now, dy dx is inversely proportional. Inversely proportional. We had some conversation about this phrase, inversely proportional. This isn't really calculus. This is something that you would have picked up in science class, maybe in an earlier math course. But if I tell you that A is inversely proportional to B, then what that means is that A, it's not equal to 1 over B, but A is some constant times 1 over B. K is referred to as your constant of proportionality. So if the rate of change of y with respect to x is inversely proportional to x, then I would say that dy dx equals k over x, where k is the constant of proportionality. All right, so what we have now is our what we have is our differential equation. We want to solve this differential equation. Okay, I see k, I see x. Let's see, I've got x on the right, I have dy on the left, but I also have dx. So let's multiply both sides by dx. dy equals k over x times dx. Since k is a constant, because that's our constant of proportionality, I'm not too worried about the fact that we have a k there. I can integrate both sides. The integral of dy, if you're not sure, remember there's a 1 there. There's a hidden 1 in between the integral and the dy. The integral of 1 dy is just y. The integral of k over x. Well, k is a constant, so I can use that property that says I can pull the k out in front of the integral. And so we have k times the integral of 1 over x dx. The integral of 1 over x dx is natural log of the absolute value of x plus c. You must have the absolute values there so that you are assured that your final answer is positive. X could be a negative number. We put the absolute values around it to make sure that we're getting a positive. If y equals 2 when x equals 1, well, that means that if x equals 1, y is equal to 2, that point is on the curve. So let's use that information. Y is equal to 2k times natural log of 1 plus Charlie. The natural log of 1 is 0. k times 0, whatever k is, k times 0 will be 0. So 2 equals 0 plus c. Our constant of integration is 2. That means we've got a better model now. We can say that y equals k times the natural log of x plus 2. Great. We use the fact that y equals 2 when x equals 1. Furthermore, we know that y equals 4 when x equals e. So this point, e4, is also on the curve. So x is equal to e, y is equal to 4. 4 equals k times natural log, absolute value of e, plus 2. The natural log of e is equal to 1. 4 equals k plus 2. K is equal to 2. So now we have y equals 2 times the natural log of x plus 2. We have a specific solution, or a particular solution. We're almost done, except we actually have to answer their question. Their question says, when x equals 2, what's the y value? Well, y is going to be 2 times natural log of 2 plus 2. Since the 2 inside is positive, I don't need the absolute values. You could leave your answer as 2 times the natural log of 2. Or you could use your property of logs that allows you to bring that 2 up. So now you have the natural log of 2 squared plus 2. That's the natural log of 4 plus 2. Since these are all numbers, feel free to stop here, or here, or there, any place you like. That's our end of day bell here at East End. And I just realized that the title on the last couple of slides were incorrect. We haven't been doing simple differential equations. We've been looking at separable differential equations. My apologies. All right, I think this is our last one. And this is the tricky one, so settle in. Determine the function y equals f of x, whose slope at all points is given by this expression right here. Well, I just told you that the function has a slope. When we talk about slope in calculus, we're talking about slope at a point. Slope at a point is what our derivative represents. So we have the expression dy dx is equal to x e to the negative y squared divided by y. All right, this one's going to take us some time. So this separable differential equations, I've got y's and x's on both sides. I have a fraction equal to a fraction. That's a proportion. I like to cross multiply when I see proportions. It doesn't always work, but let's see what happens. Y times dy equals x e to the negative y squared dx. Let's do the check. Have I separated the variables? Y and y, good, those are on the same side. I have x and x, good. However, I have this e to the negative y squared showing up in the middle. I don't like it. It's on the wrong side. I have to get that e to the negative y squared. Now, you have to do this correctly. Since x, e to the negative y squared, and dx are all being multiplied together, we're going to divide both sides by e to the negative y squared. So we have y dy divided by e to the negative y squared equals x dx. You can, if you don't like having the e to the negative y squared in the denominator, and I don't like having it in the denominator either, I'm going to rewrite this as e to the y squared y dy equals x dx. Let's see. X and x on one side. Y. Oh, I've properly separated the variables. Now that I've properly separated the variables, we're going to integrate both sides. The integral on the right, the integral of x dx, is easy enough. That's 1/2 x squared plus c. The integral on the left is tricky. This is an ugly integral. Not impossibly ugly, it's just going to take a little bit of work on our part. We have the integral of e to the y squared dy. Now I've kind of painted myself into a corner here. I don't have a lot of room. So I'm going to go off on the side here. And we've got integral of e y squared y dy. What I'm going to try is integration by substitution. And I'm thinking about that for a couple of reasons. First of all, this is a really ugly integrand. Second of all, I have no properties that allow me to do anything with integral, with functions when they're being multiplied together. All of these are good clues that we're going to try integration by substitution. In my calculus class, when we talk about integration by substitution, we usually use u, and then we talk about the baby. Where's the baby hiding? And in this case, I'm pretty sure that y squared is our baby. If we make the substitution u is equal to y squared, then we take the derivative with respect to y, and we get 2y. Our next move is we're going to solve it for dy. So dy equals du divided by 2y. We're going to go back and we're going to rewrite the integral. Instead of e to the y squared, that's too ugly, I'm going to write it as e to the u. Times the y is there for now, but watch what's going to happen. The dy is replaced by du over 2y. Those y's cancel out. That 2 is in the denominator, so I can factor it out in front of the integral. I've got 1/2 e to the u du. Because by doing this substitution, we've just made our integrand so much easier. Everybody in the class knows what the antiderivative of e to the u is. That's just going to be 1/2 e to the u plus c. And because u is really y squared, we have 1/2 e to the y squared plus c. Now I want to be careful. This 1/2 e to the y squared plus c is not your final answer. This is what we need to then jump back and insert over here. So we have 1/2 e to the y squared plus c, we'll call that c1, is equal to 1/2 x squared plus c2. That's what we have to solve. We were in the middle of this differential equation that we're trying to solve, so let's try to finish it off. I'm definitely going to need some more paper. So I've got the equation 1/2 e to the y squared plus c1 equals 1/2 x squared plus c2. And our goal is to solve it for y. Subtract the constant from both sides. 1/2 e to the y squared equals 1/2 x squared plus your constant. Going to multiply both sides by 2, e to the y squared. 2 times 1/2 x squared is just x squared. 2 times Charlie, this is super Charlie, so 2 times something you don't know is still something that you don't know. I want to solve the equation for y. In order to do that, we're going to take the natural log on both sides. Alright, and technically this should be absolute values over here, because I want to make sure that x squared plus c, if we're going to take an absolute value, that this expression in here is always positive. Otherwise you can't take the natural log. E raised to any power is positive, so I don't really need the absolute values here. Natural log of e to the y squared, I can take that exponent down in front, and we get y squared equals the natural log of the absolute value of x squared plus c. If I want to solve it for y, y will be plus or minus the natural log of the absolute value of x squared plus c. Great. What we have is a general solution. Again, because our equation involves Charlie, that's a general solution. But what I'm after is a particular solution. Pardon me, I need to go back to my notes and remind myself what the initial condition was. The initial condition was that the function passes through the point 0, -2. So, if we pass through the point 0, -2, then I have that negative 2 equals plus or minus the square root natural log x, not x squared, 0 squared plus c. Now, this is an important point. I want to put a star next to this. I want to draw your attention to this. We must determine whether we are going to use the positive or the negative version of the square root. Because when you solve a differential equation, you're looking for a function. We can't have this ambiguity of the positive or the negative. We need to decide. Now, the way you decide is you look at your initial condition. When I evaluate the right-hand side at 0, I need my final answer to be negative 2. Because I need the answer to be negative 2, we select the negative portion and we eliminate the positive. So from now on, we have the equation negative 2 equals negative, the square root, natural log, 0 squared is 0 plus c, negative natural log of c. Let's see, I can make that 2 equals the square root, natural log, the absolute value of c. I can square both sides, and we get that 4 equals the natural log of the absolute value of c. In order to solve it for c, we're going to we're going to do exponentiation. That's the fancy term for this. And so we get that e to the 4th, e and the ln cancel out, is equal to the absolute value of c. So I guess technically c could equal e to the 4th, or c could equal negative e to the 4th. So you really do have two options there if you want to be really, really specific. So your final answer should be, your particular solution would be y equals negative square root natural log absolute value x squared plus e to the 4th. Or you could have y equals negative square root natural log x squared minus e to the 4th. Yes, technically, based on the information that we're given, your answer could be one or the other one. In order to make a final decision, you'd have to be given another point. I don't want to belabor that point too much. You've done a great job. You solved a really tricky differential equation. I think this generally goes beyond the scope of anything I've seen on the free response portion of the exam, and we're good. All right, so before we conclude this portion of the video, the last thing we need to talk about is called a slope field. And slope fields is something that we introduce at the tail end of the course. These are really kind of neat. The purpose of a slope field is to help you visualize what the solution is going to look like, what the solution to a differential equation is going to look like. Over the course of the past few days, we looked at several examples of differential equations that you can't solve directly. You can't separate the variables. You can't just integrate both sides. So you need some fancier techniques. And the fancier techniques that we're going to look at is we make slope fields. Now, the graph on the right, I generated using a computer program. In the middle of the test, you're not going to be able to do this. But I want to show you how you would do this. You pick a point. Let's say we pick the point 1, 1. dy dx, we know, means the slope of the tangent line. So the slope of the tangent line at 1, 1, x is 1, y is 1. We get negative 1. What this tells me is when I draw my curve, whatever the curve happens to be, if we pass through the point 1, 1, then the slope of the tangent line must be negative 1. So if I go on my graph, one space to the right, one up, this guy here, my tangent line, must have a slope of negative 1. And I can see from my tangent line that it's decreasing. I don't know exactly that the slope there is negative 1. I don't even need to know exactly that it's negative 1. I just wanted to get a general understanding. Well, what if I went out a little bit further to the right? I went to the point 1, 2. If you plug 1, 2 into this guy over here, I think I did this wrong. I don't think this is the right slope field. No, I'm good. Sorry about that. Anyway, as you plug in more points, you're going to find you're going to generate the slope for this tangent line, the slope for that tangent line, the slope for all these little tangent lines. Generally, what we do in AP Calculus, and it makes our lives a lot easier, is we focus on horizontal tangent lines. And so when am I going to get a horizontal tangent line? Horizontal tangent means that dy dx is equal to 0. But if my derivative is equal to 0, since my derivative is a fraction, that means that the numerator is equal to 0. So negative x equals 0, x equals 0. For all points in the xy plane, if x is equal to 0, the slope of my tangent line will be equal to 0. So if this is the point 0, 1, when I plug that into my derivative, I'm going to get slope of 0, so I draw a horizontal tangent line. This would represent the point 0, 2, horizontal tangent line. 0, 3, 0, negative 1, 0, negative 2, 0, negative 3. At all points up and down the y-axis, I'm going to have a horizontal tangent line. And so that's helpful information to help you identify what the right curve is. All right, so that concludes this part of the video. What we're going to do next, I'm going to take a little water break. We're going to look at a problem involving slope fields and differential equations as it appeared on the 2006 AP Calculus exam. We're given a differential equation, and if you look at what we've got there, it's a pretty intimidating differential equation that we're going to have to solve. But we're going to do this together. We're going to generate a slope field at 9 points. And this is a very, very typical question that's going to appear in your AP exam. Then we're told information, and then we're going to finally generate a general solution. But I'm going to pause the video at this point. It's a good opportunity for you to go and get some popcorn. I'm going to enjoy some popcorn that I just purchased from Alexia Rocha. And then we're going to come back and do this video in one sitting.